slowed down. So let's get started. Continue to fill out the onboarding survey. We'll give you a little bit more time in a couple minutes.
I can stop sharing, Tasha, so that you can share your view of the slides, and that way you don't have to ask me to advance and whatnot, and we can switch to me when it's my turn.
Okay. All right.
We have the same slides you all folks have that link to.
Yeah. All right. Is everyone seeing my screen? Cool. Welcome to our first onboarding training for Cryo in the Cloud. I'm Tasha Snow. I'm a postdoc at the Colorado School of Mines. And Jessica, do you want to introduce yourself?
Hi, everybody. I'm Jessica Scheik. I'm a research assistant professor at the University of New Hampshire.
And Fernando?
And hi, everyone. My name is Fernando Perez. I'm faculty in statistics at UC Berkeley.
Cool. We also have Joanna Milstein and Wilson Satoff and Matt Siegfried, who will be helping you if you need anything. So they'll be watching some of the chat and helping to get people onto the hub. So feel free to add questions to the chat here on Zoom if you need anything at any point, and we'll check in periodically. So just a brief background on Cryo in the Cloud. We're setting this up for the ICESat-2 Science Team because it was something that y'all really seem to want and would be really useful for you. And NASA in general is moving that direction with their open science push. And so we designed a cloud computing platform with bumpers to accelerate discovery, enhance and collaboration for all of you. And so we're going to be trying to track how well this works, best practices for the community, that sort of thing as we go along. The cloud is going to be persistent for at least 3 years. We have that funding now through Transform to Open Science and through the ICESat-2 Science Team. Y'all will have access to small and medium servers for everybody. And you have the option of bringing your own AWS credits to access larger computers. So this allows you to not have to pay the fee for keeping the platform going and that sort of thing. You just pay for the AWS credits if you want to do some big machine learning projects or analysis for Antarctica or that sort of thing. So there's lots of flexibility in this. We will be developing new tools for Jupyter and for JupyterHub and for cloud computing and for your hub. And some of that will include personal cost monitoring tool to understand your usage and helping to improve intra and inter-hub collaboration tools. And we're working with 2I2C, which is the International Interactive Computing Collaboration. And they're standing up our platform, and they'll be using what they learn, what we do as a partnership to help them scale up using community surveys, feedback, and guidance. So this is kind of a model of how we're working together. So the people I mentioned at the beginning, a lot of us are part of the community leadership team. We'll be working with a community guidance team, which is James Monroe and Jim Colander, who might be Jim. I see on here. I'm not sure. I don't know if James is.
Yes.
Cool. And then we have a cloud engineering team, which is our 2I2C engineers. And so to start, I want to go over just a code of conduct for this meeting, and I'll walk us through that. We strive to create a welcoming and inclusive culture that empowers people to provide outstanding open science that requires an open exchange of ideas balanced by thoughtful guidelines. This isn't all inclusive, but here are some of our guidelines. Practice empathy and humility, participate in an authentic way, and in doing so, contribute to the health and longevity of the community. Exercise consideration and respect in your speech and actions. Assume that everyone we work with is doing their best, so assume good intent if possible. Listen carefully and actively. Ask questions and seek to understand your partner's context. Encourage other people to listen as much as they speak. Someone is not muted. There we go. Attempt collaboration before conflict. Treat other people's identities and cultures with respect. Make an effort to say people's names correctly and refer to them by their stated pronouns. Be mindful of your surroundings and of your fellow participants. Alert community leaders if you notice any dangerous situation, someone in distress, or violations of this code of conduct, even if they seem inconsequential. Being respectful of differing opinions, viewpoints, and experiences, giving and gracefully accepting constructive feedback, accepting responsibility and apologizing to those affected by our mistakes and learning from our experiences, and focusing on what is best, not just for us as individuals, but for the overall community. So if anyone has any questions, let me know now. If not, we're going to get back to those surveys. For anyone who has not yet have access to the hub, make sure you can check that and that you are able to do that. You can use that form at the bottom, the Getting Started survey, to give us your GitHub ID to be able to do that. But for everyone else, if you could fill out that onboarding survey, I'll give you 6 or 7 more minutes to fill that out. And go ahead and give me the thumbs up if you are done, once you are done with that survey.
And if you can't access the hub, please let us know immediately so that we can kind of help you after filling the survey.
Maybe I should play some music for the background.
Fernando, I see you talk, but I think you're muted.
Well, then there's that too. I was saying that I'm not sure that I know how to play music on Zoom, because I think yesterday I wanted to do it in lecture, but I think you have to flip a switch somewhere. Otherwise, I think the noise suppression kills it. I mean, I know it can be done, but I don't know. I've never tried it.
Let's see. Can you hear it? Cool. Good work, Zoom.
Oh, there it is.
Is it bad?
Yeah, pretty cool lo-fi vibes.
Classical for studying. Oops. Sorry about that. Okay, give you about 1 more minute for this. Let's see how we're doing. For anyone that joined late, we're just working on the onboarding survey here. All right. I'm going to get started. If that works for everyone. If anyone still needs to work on that to finish that, I see we got most people in already. It would be great if you could spend just a minute or two at the end of this to finish that survey. So doing a little bit of housekeeping to start, I'll point you to a few things that we have that you can keep in mind for all of this. Who can use this and how they can access it will be in some setup instructions in the Jupyter book that we have. So that'll be coming soon. You can access that. Most of the people who can access the CryoCloud right now are the ICESat-2 Science Team for the most part, and a few developers. And that will be opening up to the people who are part of the workshops, the Cryosphere people who are part of WACE, FOGS, AGU that participate in the CryoCloud training. So those are going to be who can access that, and you have already gotten some instructions on how to access. In general, there will be limitations on personal storage on the hub. We're probably going to keep it to about less than 0.5 terabyte. We pay for the storage that we have, so keep that in mind when you add data to the cloud. And this was asked about at the ICESat-2 Science Team meeting. pip installs will be possible as a user, but they will be ephemeral. You'll have to do that for each time you get onto the server. So keep track of what you're installing in your notebook. And if it's something that you use regularly and that someone else probably also uses, we'll just add that to our Docker image to make that easy. And then guidance for that will be in our workflow, but I'm here to help you. Our leadership team is here to help you, so we can do that. Troubleshooting, there is a huge group of community expertise, so you'll be able to, we'll provide you with links to community platforms for reporting issues. Pangeo GitHub will be a great place. Their discussions page for getting answers to questions. If you have issues, GitHub has our GitHub issues will be a place that you can report things, and then you can also ask people on Slack. And when you start working in this open science environment, it's really awesome because there's often people who are already working at the same time as you and who can answer your questions really quickly. And it gets to be really cool to collaborate in this way. So I highly recommend learning how to do this so that we can all answer these questions really quickly and make the CryoCloud really stellar. I wanted to put a plug for the CryoCloud. Anyone who uses this in your papers, for publishing, for your research, we have published the Jupyter book at Zenodo, and you can cite us. This is how we're going to track how successful the community or the CryoCloud is. So I hope that you'll be using that, and we'll be adding slides and other things like that to our community, Zenodo community. And then here's some links, a cheat sheet. You can access those later, but everything is here, your one-stop shop for the CryoCloud. So now I'm going to turn it over to Fernando.
Let's see, where are the sharing controls? Oh, let me stop this sharing so that I can share over here. Where are my controls? Come on, you'd think we'd have this Zoom thing licked by now. There we go. All right, thanks, Tasha. It's great to see everyone here. So I want to give a bit of a high-level overview of sort of how we are thinking about this, and a lot of this this thinking is really motivated by this papers like this one, whose authors are some of whom are actually in the room here. Jim Colliander is one of the authors of this paper. Yui Panda, one of our engineers, who's done a lot of the heavy lifting for this hub, is as well. Some of you may know Shel Genteman, the lead author. She is the lead of the NASA TOPS program. Chris is the executive director of 2A2C. I'll have a little bit more to say about that. In this paper, they sort of argue, and this is kind of backed by these tweets from folks like Shel or Julius Busicki, who's an oceanographer who works a lot on Pangeo, that the cloud really does enable certain scientific workflows that were just not viable before, right? We're not going to analyze 245 gigs of data on a Raspberry Pi at home on a $30 computer on your own, but you can now. Or Julius can work from his phone and do real analysis in the subway in New York City on JupyterLab. Now, JupyterLab UI, to be fair, wasn't exactly designed for phones, but it can be done. And this kind of mode of thinking of moving to the cloud, which is not perfect, by the way. We're advocating for this because it solves certain problems. It certainly brings other problems, but it is kind of one technological piece within a bigger story that we are, at least a number of us in here, are really big believers in, which is that science done in a more fundamentally open way is the future of science. And NASA is pushing pretty hard on this. Shel Genteman is leading the program Transform to Open Science at NASA TOPS, which is part of a larger NASA agency-wide open source science initiative. 2023 is going to be declared the year of open science at AGU. And so what we want is to begin building both the technological infrastructure and the community practices that are aligned with this way of sort of thinking about science as a fundamentally open and collaborative endeavor. The cloud can be a little bit of sort of a digital watering hole, right? I think we have today an opportunity that is shaped by a kind of a confluence of ideas. The large volumes of openly accessible, fair data that is coming from myriad sources, our ability with the cloud to put scalable computation next to the data, right? Rather than saying, well, there's a bunch of data somewhere that we can all download to our computers. Instead, we can say, no, here's how we can bring, now the computers are small, the computers are actually smaller than the data, because a computer now is really a small amount of data. Actually, it's a Docker image of a few gigabytes, which typically pales in comparison to the size of the data sets. So once the cloud industry created this infrastructure, which effectively consists of warehouses all over the world full of computers, then it becomes feasible to say, let me bring the computer to the data rather than the data to the computer. But the computer is not just an empty Linux box, right? The computer can be shaped by us by instantiating it with the set of modular tools that we want. And those tools are tools we can compose, assemble, and turn into what we need to do our jobs. And this is a bit unique, right? There's an important opportunity here, because then I think it gives us a way to come together in one place, the way kind of watering holes work in nature, which are these spaces where the common resource attracts even potentially disparate actors, some of whom might otherwise eat one another, right? But both the lions and the zebras need water, and they all have to come to the watering hole. So we want the space to be a space where we can all come together beyond traditional disciplinary boundaries, right? When we have problems that require the analysis of data that we're not going to download on our laptops because either it's too big or because it's too many different sources that vary, that require integration across multiple technologies, where we want the input and the participation of disparate and diverse communities, because the physical scientists need to work with the social scientists and with the community members, because we want to bring scientific results to the community to impact decision making, to impact policy making, to help with environmental problems. And so hopefully we can create, as I said, with these approaches, both technical infrastructure and the right community practices for this to be possible. Now, these things don't happen in a vacuum. It turns out that if you want to do something like this, you need actually human infrastructure. And some of us here in the call, and I want to kind of flag out Jim Colliander and James Monroe, are part of this organization called 2I2C that Tasha already referred to. It was created a few years ago by folks from the Jupyter and related communities, mostly at UBC, Columbia University, and Berkeley, who were facing similar challenges, which were, in a sense, what we call catastrophic success. We had all deployed for various reasons in research and education, instances of Jupyter in the cloud that were being very widely used, but others wanted to use them too. And our academic institutions were not really a good fit to start serving other communities, right? I can't go ask Berkeley, go instantiate something like what we have for teaching for the ICESat-2 Science Team. And when we saw this challenge, we co-founded this organization, 2I2C.org, which is a nonprofit organization, but that can act as an actual business. It can serve, it can provide services for interactive computing infrastructure, with the idea that we can provide managed hubs, or they can provide, I'm using the royal we because I collaborate closely with them, but they do all the hard work, managed hubs in the cloud that offer computing resources, that offer software environments and configuration that give you access to the data, and where the community can come into them. But this organization is not a startup. Its mission is to serve science and education. Its mission is to really contribute to the health of the underlying open source ecosystem. And so everything that 2I2C does is done in the open source packages and tools. So everything that we do as part of this effort, which is done, the actual services provided by 2I2C as an organization, will be contributed back. So our improvements, any problems that we solve, any insights that we gain from this experience and we develop new tools, will be contributed back to those open source communities. And importantly, 2I2C embraces a principle called the right to replicate. The right to replicate is about more than just being open source. It's about the idea that the way the infrastructure is used and deployed is such that you, the users, can decide to take all of that and do it yourself without the help of 2I2C. So not only does 2I2C not lock you into any particular cloud vendor, it's more than that. It also doesn't lock you into its own expertise, so that science can be taken and replicated elsewhere by others. Obviously, that would require that you do some work on your own. 2I2C provides enormous amounts of expertise and know-how, but there's nothing that is being kept secret or in the back to lock you into their infrastructure. And we think that's an important principle to embrace. So as a kind of motivation, proof of concept of the kinds of workflows that we'll be doing, I want to tell you a quick story of a course that I teach at UC Berkeley called Collaborative and Reproducible Data Science. I taught it this past spring. And it's a course that's motivated by a quote that I've used a bajillion times in presentations. Some of you may have seen it. It was by Buckheit and Donahoe, who were paraphrasing a geoscientist called John Claerbout at Stanford, who said that articles in computational sciences are ultimately advertisement of scholarship. They're not really the actual fundamental scholarship. That is contained in the complete software development environment and the complete set of instructions that generated the figures. And if we update this quote for the complexities of today, this quote was written in 1995, when effectively they were saying, if I give you the MATLAB package, the zip file with the MATLAB package for the paper, you have everything you need. The world today has a lot more than one MATLAB package, and so we probably need a place that is properly configured to run all of this code. And that's what this course tries to do, is teach students how to conduct their research in an open, collaborative way that leads to these kinds of outcomes. And this includes teaching them both concepts, ideas, and practical skills. We teach them how to do version control with Git, how to automate their workflows with a programming language instead of clicking on GUIs and run them through scripts, how to test things, how to share their outcomes, how to document their work. And we do that by ultimately guiding them towards saying all of your work ultimately can be shared with others if you do it in the right way, if you do it in a GitHub repo that has markdown documents, that has mathematics, that has code, that has notebooks. You can publish it with Jupyter Book. That is the tool that we are using for documenting everything here, and it's installed on the hub. And Tasha already showed you a quick link to the Jupyter Book for the Cryo in the Cloud system, which is where we're documenting what we have. And ultimately, if the work is done in that fashion, you can share that same contained workflow with a tool called Binder. Some of you a number of you, I'm sure, are familiar with Binder. For those of you who are not familiar with Binder, it's a tool whose job is the following. It takes a GitHub repository simply that follows good practices, that declares its dependencies explicitly, and by putting the link to the GitHub repository on the mybinder.org user interface, you click a button and you get a new URL that says, this is that GitHub repository turned into a live server that has all those dependencies and that is deployed in the cloud. And that is the kind of infrastructure that ultimately we are using here that would allow you to make your own research when you have finished publishable outcomes to be more easily shared with others in a way that is reproducible. Students learn in the end to kind of integrate their research into compendia that have a main narrative notebook, right, but that also have underlying analysis notebooks that have data that is either linked or included, that have tests, that have proper reproducibility support, and that lead to these kinds of things. So students end up publishing their compendia as little books like the one we have for the Cryo in the Cloud, right? But these little books have not only the complete scientific narrative. By the way, this was one of the best projects that we had in the spring, was our students analyzing the air quality in the Bay Area from the 2019 fires. This is actually a picture of the Golden Gate yes, I think that's the Golden Gate Bridge. It's actually hard to, yeah, this one is the Bay Bridge, and this one is the Golden Gate. That's what San Francisco looked like 3 years ago, around this time, a few weeks ago. And so here's a scientific story that you're telling your audience, right? Where you have results, you have tables, you have figures, etc. That same book contains all of the underlying analysis notebooks that have all of the details. There's the underlying code in the GitHub repository, and by providing your users with a single link, an identical environment will open in the cloud, not in the hub where the students were working, which is a hub just like ours, but it'll open in the cloud, and then anyone can see a live version of that book that runs in Jupyter Lab. And so this is the kind of workflow that we're kind of aiming to give people, where we go from exploration to sharing effectively what can be complete research compendia with the community. And I probably should mention at this point, I forgot to put a slide about this, but AGU, some of you may have seen that AGU has a new program called Notebooks Now. Several of us here in the call are part of the steering committee for this project, and AGU is basically elevating the idea of publishing research notebook as primary elements of the scientific record. And so we're trying to help you basically do all of your work from the beginning in an environment that facilitates this kind of approach. But to do that, we have to serve you with something that lets you do really all of your work. This is not just about notebooks. We want to give you something that is, first of all, as similar as possible, whether you're working in the cloud in a hosted environment, which is going to have a number of tools that we're going to go over now, or whether you're working on a personal system. Okay, so because even though we are advocating for the cloud as probably the place where a number of things are possible that you can't do more easily on your system, whether you need to access very large data sets, whether you want to be able to turn on a computer that's bigger than your laptop in terms of memory, whether you need to parallelize quickly over a cluster and you want to instantiate, say, 50 nodes or 100 nodes, there's a number of things you can only do in the cloud. But it's also important to know that within reason, that same environment can be replicated on a personal installation, so that when you're on a plane, when you just want to do some lightweight editing, when you're up offline on a desert island, you can have as much of your research as fits on your laptop in a way that is a smooth continuation of the remote hosted experience. And so one of the tools that we use for that is JupyterLab. If I could have a quick show of hands, let me see how I can see participants. If I could have a quick show of hands, how many of those who are in the call have used JupyterLab? If you could raise your hands or give some positive sign, just so I get a sense. Okay, so we're a little bit over 50% of you who have used JupyterLab. So for some of you, this is going to be slightly repetitive, but for those of you who haven't, I presume by now the majority of you probably know what Jupyter Notebooks are. For those of you who don't, Jupyter Notebooks are documents that contain both code and text code and human narrative text in a natural human language that can include figures and multimedia and mathematics, but also code and the results of code. But JupyterLab is an environment that evolved from the web-hosted notebooks into a richer workbench precisely for these kinds of workflows that we have here. So when you land in JupyterLab, which we're going to see in a minute, what you get is an environment that looks like this, and that lets you work at the terminal, that has file managers, that lets you access markdown files with live previews, that allows you to launch other tools that we're going to dive into a little bit, including some of those tools may actually be hosted within JupyterLab itself. There's a little diagram editor. I don't remember if we installed that one on this, but we can add other tools as needed. It has data viewers for multiple data types built into it so that you can quickly take a look at your data. But it also allows you to do other kinds of computational tasks that you may need without leaving that environment. So if you need to open a desktop, and we'll take a look at this, you can open a virtual desktop. It's basically a Linux graphical user interface that opens into the system, and we can configure that further as you tell us what tools are missing, what things are needed. We can add those. We have a tool installed that if we have time, I'll dive a little bit into, called SyncThing, which allows you to synchronize files either between machines or even between machines and your local between hubs, between users on the same hub, or between folders on the hub and your own system. Think of it as Dropbox, but it's free. We haven't used it super extensively. I haven't tested SyncThing sort of in anger with multi-gigabyte data sets. So we'll have to experiment sort of how robust it is if we put enormous pressure on it. And I'm very interested in learning how it goes for people, but I do use it regularly for lightweight things, and it is extremely convenient to use for lightweight things, because basically you can designate any number of folders on the hub that you want to share, and then you can install a local client that runs on Windows, runs on Macs, runs on Linux, and on your laptop, on your desktop at work, you have whichever folders, and you want to connect this folder with this one on my laptop. This folder I wanted to show up on my desktop at work. I want to share this folder with my collaborators, and those folders act just like Dropbox, right? You put a file in one of them, the file shows up on all of them. And so that takes away a lot of the pain of moving small amounts of data. Obviously, you don't want to do that with the 10 terabytes of cloud data that you're going to be analyzing. But if you need to grab a few images, if you take some screenshots of your laptop and you want them to show up over there, you don't have to be constantly figuring out, how do I FTP things into this thing? Where is it on the cloud? How do I drag and drop things? You can just basically have it happen. And so the idea is that we want to give you a workflow that, in as much as possible, and this is kind of the reality for me now, that I have environments that look very, very similar, whether I'm on my laptop and I basically have to look at the URL. Does it say localhost Okay, that's my laptop. I'm working on Jupyter on my laptop. Does it say NERSC? Okay, I'm at a supercomputer up at NERSC. And does it say berkeley.edu? Okay, I'm on the hub on campus. Does it say Jupyter Earth? Okay, that's our NSF-funded Jupyter Meets the Earth project, which is how I began collaborating with Cryosphere scientists, with Jessica, Matt, and Tasha and Shane a few years ago. Or am I in the Cloud Hub? But these feel, to the extent possible, like one and the same, right? They feel, to the extent possible to me, like a single environment. And so I want to go a little bit. So first of all, thank you. We want to make this fairly interactive. We want to leave plenty of time both for interruptions and for a lot of questions. So please either ask in the chat and others can help as we go, or just holler, right? We have a small enough group that you should be absolutely free to interrupt us. I want to make sure, first I want to thank Tasha for putting all this together. She deserved, by the way, a huge round of applause. Just to give you a bit of a story, this idea all came to be when Jim Colliander and I were in Vail for another interdisciplinary NASA-funded project from heliophysics. And Tasha came up to meet us in Vail to kind of brainstorm how could we turn a little prototype of a hub that we had instantiated for that 1 week long event for NASA into something more lasting for the cryosphere community. And out of an afternoon of brainstorming at this workshop in Vail, Tasha turned it into two proposals, one that she shepherded with the ICESat-2 Science Team, another one in parallel with the NASA TOPS team, has basically become kind of a cloud engineer on the quick in the last few weeks by doing absurd amounts of work, and has collaborated with the engineering team at 2I2C. And on the other side, Jessica, who has been leading the development of IcePix for the last few years. I first met Jessica at the first ICESat-2 Hack Week at UW. We talked about the possibility of collaborating on maybe building some tools to help with the ICESat-2 data access. And Jessica has led that project in incredible ways. And for me, this is super satisfying. I wanted to connect with this community. I wanted to learn about the science and see how we could work bring our tools to the world of cryosphere research a few years ago. Folks like Jessica and Tasha have been incredibly welcoming, and now they're kind of leading this. And so thank you both for the great work you've done. And for all of you, I hope this will be useful. Let's hop in all on the hub. Please let us know if anyone can't. Right now we need, Matt, if you have a question or a comment, please speak up. Matt Siegfried, I see your hand is up. Was that an accident?
I'll contribute a little bit more here. So Weiji is on the call and he has been helping a tremendous amount with putting this hub together as well. And it's all been voluntary. So I wanted to give a huge round of applause for him. And also Wilson Satoff and Joanna Milstein have been doing a ton of work on the book and everything as well. And a lot of this came together because Joanna came up with this idea of a cloud with bumpers. And so she should take a lot of credit for having the CryoCloud here for you guys today.
So let me log out of the hub. So if you go to hub.cryoonthecloud.com, this is what you should see, right? If you go to cryoonthecloud.com, you land here. And thank you, by the way, for the absolutely wonderful, I love the website. And so the two main points of accessing Cryo in the Cloud right now are documentation, which is built with JupyterBook, this tool whose kind of workflow we're talking about. You can see this is kind of following exactly the workflow that I was mentioning for the class. There is a GitHub repository that contains how to build that hub. It's in our GitHub organization. And so when you land here, this takes you to the documentation. That documentation is structured as a JupyterBook. It's very much a work in progress. I have to admit, I was hoping to have written down more of what I am demoing today, but we ran into a few issues. The cloud, we're advocating for it, but we're not selling you snake oil. We know there's a lot of rough edges. There's things that we got mired in a few like weird AWS credentials issues for accessing USGS data buckets, and we don't know what it is. And so we've struggled ourselves, but our plan is to continue developing this Jupyter book by by turning it into effectively the community documentation reference that you can all use whenever you need anything. And if you click on this one, that's actually the hub itself, which should take you here. When you click to log in, I've already set up my authentication, but all of you should be able to see this when you click on that. If you don't, obviously you're not going to have all of this open. Let me close all of these things. Let me shut everything down so that you start kind of with a clean environment. Let me shut everything down. Okay, let's shut down all the kernels. Oh yeah, here we go. So you should end up with something like that. I already have some files. You might have a few less files here, but this is Jupyter Lab. Okay, so Luis Lopez, it looks like you have not been added to the list of allowed users for this hub. Please, so Luis, what we need from you is your GitHub ID. And so if you give us your GitHub ID and you can just paste it right here in the chat, thank you, Luis. So we will add you right away to the org, and you should be getting an invite to be on the org. So just so you all know, yes.
So that might also be in your email inbox because, or it may have been, the invite may have been expired. I think we've added you, but.
You might have missed the first email for the invite. So yeah. Joanna just sent you a new one. For reference, this is what's happening, okay? And this is useful for you to learn and understand. Do we have to SSH every time we want to connect to the lab instance we were working last time? So there's no SSHing here. In fact, I don't even know if you need SSH access. You can let us know. I don't even think that we have actually turned on. There is SSHing into cloud instances a little tricky. I don't know if we've turned on SSH access, but if you mean, do we need to log in, connect to the lab instance? They do get, if you leave them idle for too long, they do get shut down. Your files are persistent, but the instances get shut down. So you do need to reconnect into it to kind of get back to where you were. I'm not sure if I'm answering your question correctly, but feel free to Abhijit, and correct me if I'm mispronouncing your name. Feel free to just open your mic and speak up if I'm not answering your question correctly, because I may not be understanding what you're after.
Well, I believe we are using OAuth to basically connect to the board instance, right? To the compute instance, right?
Yes, and the OAuth, that's what I was about to show, is based on this list. So in the GitHub organization that has our public information and our repos, there's a team called CryoCloud users. That's what Luis just got an invite to add for. All of you had been added before. And anyone who is in this, so right now it says one pending, Ellie, and 40 members. And anyone who is I can't remember how to read see the list. Anyway, these 40 people, 40 members here, that's the link. So these 40 people are all of you, and a few who may not be here, when are on that team. Whoever is on that team, when they try to log into the hub, they get, we use OAuth with GitHub, and they have the authorization to log into the hub. So that's how it works. Please continue.
So like whenever one of the members can basically collaborate and view others' work, that means, right? So if we don't have individual SSH into one lab work or a Jupyter lab which we are working, so basically all the members can basically check or can view or collaborate with others' work that they have been working previously.
I apologize, but I'm having a hard time with the audio, and it's broken. Just I'm getting a little bit of a broken audio from you.
Yeah, I guess I have internet issues. Yeah, but I think I got your point. I was just curious, like, let's say I have been working on a Jupyter Lab instance, and so this makes sense. Like, it's all of these 40 members which are currently added will be able to view my the previous work that I've been working on the Jupyter Lab, right?
Okay. So no, an important point. By default, no, that's a really good question. So by default, when you land in, if I understood you correctly, by default, it is a little bit different from a kind of a classic supercomputer that you SSH into. This is the home directory that you all see. One of the tools, and let me jump a little bit ahead of the presentation. If you click on this, you get a terminal. You get like an actual terminal, as if you had SSH'd in, but that terminal is in here. And where am I? This is my user. My user is Jovian. My Unix user is called Jovian. And so is, and the same is true for every one of you. We all look the same. Our home directory is home Jovian. If we go one level up, who is there? Only Jovian. So this is not like a supercomputer where you think of, okay, these are the users, and when I log in, there's home directories, and everybody has a home directory, and they're all next to one another, and I use Unix group permissions to share with one another. This is one of the important differences between the cloud and traditional HPC facilities, and I'm glad you asked, is that they look a little bit different, because what you have here is a Docker container, which is identical for everyone. We're all running effectively the same computer, if you will. We're running the same Docker image, instantiated on otherwise physically identical machines, assuming that you all chose to start the small one, the cheaper one, right? Which, as we said earlier, we would like you basically use the smallest one you need. Use a bigger one if you need a bigger one, but don't turn on a bigger one just for fun because they're more expensive to run. So if you are all running on that, we're all running on identical computers, somewhere on a rack, somewhere in the West Coast of the United States, than an Amazon warehouse. But those Docker containers are instantiated, again, their home directory is mounted from a common file system that has everyone's home directories, but you don't see the entire file system. So by default, when you're logged in here, you only see your home directory. You don't see the others. And so there are mechanisms to share, and we'll get to that. And there's a hint of those in here. I'll get to those in a minute, but it's not automatic that you get to see everybody else's work. In a sense, by default, your work is completely private, and it is as if you were in an HPC facility with Unix permissions of read-only home directories and with no ability to change permissions on your home directory. But we do have other ways to share data that we'll get to. Does that answer your question, Abhijit?
Yeah. Exactly what I was trying to understand. Yeah.
Okay, thank you. And obviously, James and Jim, please correct me and just feel free to speak up if I say anything that's not quite right on regarding the infrastructure. I'm very happy to be interrupted, by the way, folks. I'm very, very happy to be interrupted. Okay, so where were we? So for those of you who haven't seen JupyterLab, as I tried to kind of briefly summarize in the slides, it tries to be an environment that gives you complete access to compute resources. We don't have time today for an in-depth tutorial of JupyterLab, but at least I want to show you a little bit of a high level tour of the features that you will find here that can help you get the job done. So the most basic entry point for JupyterLab is I want to have a notebook. If you click on something like this, you get a Jupyter notebook that looks like a traditional Jupyter notebook. You type code here, it executes. You type Markdown, text, math, right? And you hit Shift Enter and it renders. This is your classic Jupyter notebook, right? That some of you probably already have seen. When you try to save a file, it asks you to rename it, first notebook, and now you can keep working. Those files go here. This is your home directory, as we said before, but JupyterLab is more than notebooks. You have a file browser on the left that allows you to go looking around and opening files locally. You have a little like bookmarks manager here called favorites. We're going to get to what this thing is a little bit later. It's important. If you want anything to show up here, because you may be buried deep in files here and you may want to have a few folders that you want to be able to access easily. If you right click on something, you can say add favorite and that folder will show up there and you can remove it from favorites here later. So things that you want to keep access to commonly, you can put them there and they will show up here regardless of where you've navigated, where you've navigated in the file browser. So this is what the left part does. This little left pane, you can turn it on or off. You can collapse it by clicking on this. The left pane also has a few other things. This one is important. This one is what's running. It's like a little stop. Maybe we should use a different icon, maybe a little runner. But this is the current icon. It shows you what do you have open, what compute kernels are running. So the way Jupyter works, when you have something like a notebook, or there's a few other things that can activate kernels. A kernel is the Python process or the R process or the Julia process, or there's about 100 different implementations of kernels in many programming languages that actually runs the code. So when I type here 1 + 3, somebody has to compute 4. That 4 is computed by a kernel. So this is the open tab of the document, the notebook. This is the process, the Python process called the kernel that is running, right, my code. And when I say x equals, for example, that, and I didn't finish, I accidentally bumped my keyboard, that error message came from that Python process. And here you have the terminals that you have open. This is the Dask dashboard. We do have support for distributed computing. We don't have full support for external clusters yet. We will work on that, and we will add that. But you can use Dask, which is a tool for distributed computing. We're not going to have time to get into that today in depth, but I want you to know, and for those of you who use Dask, that we do have the Dask, the basic Dask machinery is installed. I ran some basic tests, and the basic ones work. So at least on, for example, on one of the big machines, you can use Dask with local in node workers and parallelize over a single node. There is a little bit, there's a small Git, it's kind of a basic Git management tool. I tend to be a Git command line person, but I want you to know that you have this here. Jupyter notebooks have a table of contents in here, which we'll see later when we open the larger tutorial. And this is for adding extensions. We won't get into that today, but at least so you know what are your tools here on the left. And on the right, you have the ability to edit and configure metadata. For the notebooks, this is a bit of an advanced usage of Jupyter, but I'm happy to explain if anyone's interested. And there's actually a debugger. So we actually do have a Jupyter gained full-blown debugging capabilities recently. And so these are the tools on the right if you need them. This is your environment. And whenever you click on the little plus, you get this thing. The launcher is the thing that gives you access to the tools. Now, Jupyter Lab, because it was meant to be more than just a rewrite of the classical Jupyter Notebook tool, but rather a tool to do to live and do all of your work in a hosted hub, gives you access to, for example, data. So here's a folder where I have some data files, and I have here a markdown file. So I can open not only notebooks, but I can open text editors. It's a regular text editor, right, that edits Markdown. But Markdown files can be viewed if you right-click on any file. You can say, I might want to see this file, not opened with the editor, but for example, as Markdown. And so this is that same file rendered. And so as you are working, you can put them side by side. If you grab one of these tabs, you can move it and kind of lay out your workspace whichever way you want. And so if I put this thing on the side, and because I'm trying to use a screen size that is sort of recording friendly and laptop friendly, not my giant monitor, but this works much better if you have a bigger screen. So let me collapse this for a second. As you edit, the preview is live, and so you can edit LaTeX files, you can edit Markdown, you can edit R Markdown files, you can edit Python scripts, etc. Right? If you open a Python script, this is, for example, the very first IPython back from years ago. Let me put this back into a single file. Right? It's a little Python script. This you can edit regular scripts. You can edit C files, C++, Fortran, etc. I do believe, I think we have the Fortran compilers installed. We can double check. If anybody needs Fortran codes, we can definitely install a Fortran tool chain. If you have CSV files, it has a built-in CSV data viewer so that you can quickly get a sense for what does your data look like before you begin messing with it, loading it. But of course, you might say, well, I need to see the headers, or there's something weird. You can always open any file with a raw editor. So this is the same file, right, being viewed as raw data or with the CSV viewer. It knows how to view PDFs, for example. And so this is a paper by, I don't know if Shane is here, but it's a paper by Tasha and Shane and other co-authors. And so you can view PDFs. If you're compiling a paper, you have a PDF you're generating a PDF from LaTeX, you can view them right in there. Images load by default, SVGs load by default. JSON files, if the system understands the schema for the JSON files, it can show them directly. So this is an example of how to view the same JSON file, which is a Vega-Lite visualization as raw JSON. You can see it, you can view it as structured JSON, right? Or because it happens to understand this schema, you can view it as a plot. A format which is of interest to folks in here is GeoJSON. So this is an example of loading a GeoJSON file. And so that rather than viewing it like this big giant mess, right, you can view that same GeoJSON file as with the right polygons on a overlaid on an OpenStreetMap background map using the Leaflet JavaScript library that allows you to zoom and pan, and so on and so forth. This happens to be in Greenland. This is taken from Tasha's and Jessica's tutorial that you will see later. So the idea here is that JupyterLab is not just about notebooks. It lets you look at data. It lets you work in a terminal, right? Let me close all these things. So I encourage you to set your environment in a way that is conducive for you to living like with your aliases, with whatever you like to have, with your configuration. You will see you can change the terminal theme. You can choose it to be light or dark. I like my terminals with a dark background, so I always change this, right? And so now one thing that I learned quickly that I should do, because I have, remember what I showed here in this slide? Well, it kind of gets annoying to start finding, I want to feel at home wherever I am. And so it kind of gets annoying to have to configure everything from scratch all over again. So I want to point you, and I'll add these links to, where's my hub here? I'll add these links later, but I have a system. I have a system based on two little repositories that take me about 1 minute to clone. One is called in my GitHub, and you can fork this repo and update it for your config if you like this approach. But once I did this, it takes me about 2 minutes to set up on a brand new hub that doesn't have any of my default conveniences and the things that I always want to find on a system. It takes me about 1 or 2 minutes to do it. The instructions are here. I won't have time to go into them, but basically it's a repository, and you can, now that I know what to do, I just copy at the bottom. I have the Bootstrap links. I open on a new hub, I copy this, and then it clones this repository, and I have a repository on the hub that is a special Git repository that has all of my configuration for the hub, all of the things that I like to have, my shell configuration, my aliases, a few scripts that I need to have everywhere, tools that I'm used to, that I've kind of carried on my Mac and Linux laptops for 10 or 20 years. They're all there. They all show up in 10 seconds. And the other one is a companion repo. And there's a reason why there's two of these. No, it's F Perez, home setup, that does kind of the same thing, but for my scaffolding, my home directory. And so I have these two repos. One is for the configuration. The other one is for my home setup. Basically, I go to, when I land on a new hub, I go to these two repos, and both of them, I copy the little link at the bottom, I hit paste, and I'm good to go. It takes me, literally, it took me 30 seconds to configure this hub when it went live into something where I felt at home instantly, right? And so, and I encourage you, I made these two repos for teaching reproducible workflows in the cloud for my class, right? And yes, you can use a different shell if you would like. If you like Z shell, you're welcome to it. You can configure it. I happen to be still a kind of an old-fashioned bash user, but you can configure this in any way you want. This is just the scaffolding, and this can be done in other ways, but there's a couple of Git tricks that I don't want to get into in how these repos are set up that actually finally made me happy with this. And I actually had tried to do this in the past in other ways, and I always found little wrinkles that I didn't like. This lets me literally in 30 seconds be happy, and it also lets me have all of that be Git controlled. So I can actually, if I realize that I want some, maybe another alias, maybe I want to add a utility script, whatever, I do it in one hub, I push to Git, and on any other machine, I just do Git pull, and then my configuration is replicated thanks to Git on any of the number of hubs that I may be working on or my local system. So my laptop feels the same as my supercomputing environments, as my campus environments, so on and so forth. Okay, so and these little things are important. We tried to make the environment a pleasant one for working at the command line. So for example, we have Midnight Commander, MC. This is an old school tool, but I want to mention it because some of you may not know it, and you may find yourselves trying to do file management on the system. And the file browser here on the left is not a file manager. The file browser on the left is really just to like find the things that you want to open. But if you need to start doing lots of things, like I need to move a bunch of folders, I need to access other data files and copy them from here to here and so on and so forth. This is an old school tool called Midnight Commander. We don't have time to give a tutorial, but I encourage you, if you're going to live often in remote managed hubs, to learn how to use it. It can save you enormous amounts of time. And once you get used to it, it's actually better, in my opinion, than the graphical file managers of Mac OS and Windows. I actually use MC on my normal machines. I open it in a terminal on my Mac, and that's what I use. And it's installed for you so that you can use it. You can use it there. We've tried to give you the comforts of home. There's text editor. There's not only VI, but Emacs and Nano and other tools. Git is fully configured, and a number of other command line tools are there. You can let us know if something is missing, and we'll get to how to communicate with us if things are missing in a minute. But hopefully this gives you a sense that between the text editors, and in here you can access, if you want to create a new text file or a new markdown file or a new script, you can do it from here. So this is how that you will open the text editor with a new untitled file if you're not going to edit one that was there before. So hopefully this shows you that yes, you can have notebooks, but you can also have kind of some of the regular trappings of home, if you will, to get your job done. Now, some of you may need a tool that is not available here in JupyterLab, right? What if you need to load up QGIS and you don't want to start uploading and downloading a bunch of files? Well, if you click that link, this link right here that says desktop, it will take you here. And I encourage you to say use default config. This is a graphical user interface. It's a Linux desktop. For those of you who are Linux users, you will recognize this is the XFCE desktop manager. If you haven't used Linux, it's just yet another like window manager with little 4 virtual desktops, your home directory here. And so you will notice that the home directory here is the same one: demo data, dev, local, shared read write, USR. That's what you were seeing here, right? This is just a view on that same computer with regular terminals, right? And I hadn't configured anything, so these have a dark background, but it's the same files, my same aliases, the same exact stuff that you had before is here. And we have installed QGIS. We can install, I'm only a lightweight user of QGIS. I don't have any demo prepared, but I wanted to show it because I figured that might be one of the graphical user interface tools that some of you might need. Another thing that is very helpful is having a local web browser. The reason why that's useful is because you might be testing something that needs local access to HTML files, to CSS, or you're serving on the local server something with a static website generator that uses Hugo or any of these things that need local access to files. And the problem is, if I have an HTML file here with a bunch of CSS and I try to access it here, it's not going to render correctly. It's not going to work correctly because there's complicated URL proxying issues. I don't want to get into the details. It's kind of messy. I'm happy to get into those details, and I have them documented because we teach that in our class on how to get around some of them. In some cases, there's easy workarounds. In other cases, there's not. So if there isn't an easy workaround to these issues of I'm trying to look at some HTML files and they're up there, but when I try to open them, they don't open normally because all of this, it's mostly the security mechanisms of the web that have to do with how base URLs are rendered and how domains are checked and whatnot, get in the way. That is one of the issues that's a pain in the neck in the cloud. So for some tools, we can show you how to work around them. And once you know what the workaround is, it's easy and straightforward. We have a URL proxying system in there to help attenuate this problem. But there are things for which the workarounds will not work. Well, You open them on a web browser that is running locally. And this web browser can open a local HTML file and it will see it. It will show it to you right there, and you can click on it. It has the web. It can go to, I don't know, cryointhecloud.com, right? And so it can go here. And of course, we could be very meta and very recursive. Oh, interesting. This web page doesn't load. I wonder why. Okay. Interesting. Okay. I have no idea why that particular one. It may be there may be security restrictions. I'm actually not sure. Not that we need to start going fractal with a recursive login of the hub. But the point is, you have a normal web browser. You have QGIS. You have kind of access to normal. If you need anything that opens a live window, that opens a GUI, that needs local access to kind of the real computer, you can do it through these mechanisms. Jovian is not on the sudoers list, right? No, Jovian is not on the sudoers list. And so we will get to, let me make sure that we get to how to configure add packages to the hub in a minute. So Luis, if you can hold on to your question for a few more minutes, I'll make sure to get to it, because that is obviously an important question. But no, you're not on the sudoers list. The normal user is not on the sudoers list. The Conda environment and Conda now serves a bunch of does serve Jupyter tools. The Conda environment is writable to you, which means you can add a tool to Conda. And if it's a desktop tool, QGIS, we're actually not using the Ubuntu QGIS package because it's really old. We're grabbing QGIS through Conda. And so you can go to the terminal and Mamba install the package, but that will not survive a restart of the hub. You would have to do that every time you log in, because that volume, and James, correct me if I'm wrong, but that is the volume that is usable, writable, but doesn't survive restarts. Is that correct? Yeah. Okay, that's what I remembered from prior experience. I think anything pip or non-root tools can be installed locally, but would be ephemeral. Yes, exactly. That is correct. You can actually make pip persistent. There's a way to make pip persistent, but it's very dangerous. It's to tell pip to configure pip with pip user equals true, and then to send pip to your home directory. The problem is, as Yuvi has reminded us multiple times on Slack, the moment you do that, you forget about it, and 2 months later, stuff breaks, and then you find out, why is nothing working? And the breakages can be super weird. I've actually complained a couple of times to the UC Berkeley staff on Slack the night before a lecture, why is something not working? And then one of them like, what the hell did you put here in your home directory? Why is this package getting in the way? Like, whoops, I pip installed something a few months ago because I needed it, and I left it persistently in my home directory, and then it got in the way of something. So if you know what you're doing, you can do it, but I'm supposed to know what I'm doing. Technically, that's not true, but people think I do know what I'm doing, and I always do get in trouble with this. So Yuvi is right. The pip user equals true trick is super, super dangerous, but you can create environments in your home directory. Okay, so we've gone over this. I want to show you this sync thing business, right? Because at least, as I said, I am not an expert. I haven't configured it on this one. Allow anonymous usage reporting. Let's say, sure, this is an open source tool that I trust, and I will allow them to do this. So this is what sync thing looks like. Okay, the sync thing. There's a way in which it's not quite as simple as Dropbox, in that Dropbox is one folder. You have the Dropbox folder, and that folder is the same on every system that you install Dropbox. Syncing is a little bit more complicated. You have to designate which folders you want to share, and you have to designate which machines you want them shared with. It's not like you install Syncing on your home computer and the hub, and automatically you see the same thing. No, you have to say, I want this folder shared between these two machines. So it appears a bit more complicated, but on the other hand, that gives you a ton more control, because you can say, down inside of this project, I want this folder to be shared, and that folder is where the collaborators drop data files, rather than having to say, well, we have the Dropbox thing over here, and then I have this, and if I want to find it always, I have to keep track of both, or I have to link them, or I have to keep copying back and forth. And so the way you use SyncThing, and I don't have time for a full tutorial, is you basically in here, you define which folders. It has a default one that starts on shared, but you can add new folders. You can say which one do you want to share. And then in any devices, this is in particular the hub, but I have on my, where is the icon for SyncThing? Okay, somewhere here on my desktop, I have that same application, and my current desktop, I'm on a Mac at home right now, would appear as a remote device if I connect it with this one. And then whichever folder I configure appears in both. And it otherwise works like Dropbox. You drop a file in one and it appears in the other. And I use it for convenience, just like downloading things at home and putting them there. Now, for quick and dirty things, I do want to let you know one thing. This file manager supports drag and drop. So if I go, let's see, if I go to my downloads folder and something that I have here, let's say this. So if I grab, let's say, this little IPython 0.0.1 script, you can see that one, but I have my local downloads folder open. I'm grabbing a file and I'm dropping it here. Now you see a new file appeared, right? And actually it says in a few seconds because of clock differences, I guess. And so you can drag and drop pretty big things. I've dropped a few hundred megabytes like zip files into this. And the same thing, any of these files that you want to grab for local usage, you can right click and you can download. So for single files, for simple things, for uploading a zip file, this does the job. SyncThing lets you set up more complicated workflows. Okay, I don't know. Okay, seems to be back alive. So if you start using it, let us know how it goes. As I said, I've used it quite a bit, but always with lightweight work. Just convenience, quick synchronization of a few files, never with really heavy duty workflows, and never with multiple people doing a lot of collaborative work on one folder. So we will learn, and hopefully it can stand to more stressful testing. One more thing that I want to cover before I hand it off to Tasha and Jessica to go over the actual more like a more in-depth example with data analysis is, okay, well, Git, right? I have repos. How do I access, let's say that I have the website repo here, right? And let's say that I edit the README file a little bit. So this is here. Today, we're making progress. And I want to edit that file, and so I have some changes in here, and I want to send them upstream. I have both my fork and the upstream project fork available here. Which branch am I in? I have this little utility that tells me what this branch is. I didn't come up with a name, by the way. I'm sorry, but that's what Git WTF is called, but it's extremely helpful. It's a little Ruby script that tells you what your branch points to. So my main points to the remote upstream main branch. So if I commit the README and I say git push, it doesn't let me, right? Because I don't have access to the repo by default. I do have write access over there, but it's an HTTPS. It's an HTTPS repo, and it's going to say, no, you can't access it. This is where this thing comes in. So you can all find this shared folder. Whoops. Is it not there? Wait a second. I thought I'd put it there this morning. Oh, no. Okay, it should be there. Can you confirm that you all see this little notebook called ghauth if you go to shared. Okay. Interesting. Yeah, I wonder if maybe I deleted it by accident. Who knows? Okay, I just put it back. So this is what this notebook does. This is a notebook that I keep around and that does one thing. Let me go to simple mode. By the way, this is a convenient thing for the JupyterLab. If you ever have one document and you have a bunch of open tabs and you want to focus on one thing, click here on simple. It just maximizes and shows you only one document at a time rather than all of your open tabs. So this notebook uses, all you have to do is run this one cell. And what it does is it creates a tunnel between the hub and GitHub that is authenticated. Once you authorize it for your user, it creates an authenticated tunnel between the hub and GitHub that allows you to push and pull for 8 hours. Now, on first usage, you will have to click on this link and configure what repositories do you want it to allow it access to. For those of you who have write access to the Cryo in the Cloud organization, it's been pre-configured. So for the Cryo in the Cloud organization, that tunnel has been pre-configured. But you may say, I want to be able to push and pull from my personal repos, including private repos. So what you say is you go here to configure. In your case, it might have a green install if you've never added it to any account. And you can add it to any organization that you want. So I have it. These are all the orgs on GitHub that I belong to. It's a lot. I have already added it to Cryo in the Cloud. So you don't have to do that. You can add it to other organizations, or you can add it. Whoops. You can add it to your own personal account. Whoop. Here. Oh yes, it's going to ask me for my one-time password. Let me open the authenticator. 781.048. Okay. And so here, what you will need to say is, which repositories do you want it to be allowed to access? You can either say all of my repos, or you can say, nope, I want this hub to be allowed to push and pull from the following repos only for safety, right? So you get to choose which organizations, and on those organizations, whether it's your personal account or other orgs, which repos the tunnel will open to. And when you run the cell, that's why I keep this one in my favorites, because if I'm going to do any work on GitHub, I just do this. You run the cell and it says this code has been copied to your clipboard. You have 15 minutes to go here. Click here and this page opens. You hit paste and enter, and this happens. And you click on the big green button. And when it says all set, you can close this, you wait a minute, and when you get the green, you're done, and you can close this notebook. And now, if I say, let me go back to where I was. If I now git push, whoa, it's
You're still getting the error because I believe you're trying to push to the main branch, which is a protected branch.
Oh, thank you. Yes. Thank you. So let me, yes, I made that on main. So get. Are all branches? Okay, we'll figure out my permissions. Oh, wait a minute. This worked last night. Huh. Okay. The joy of live demos. Why is this? Why am I getting a 403? I literally used it last night. Okay, I'm not gonna waste Tasha and Jessica's time for the tutorial debugging this. This was supposed to work, but folks, these are the joys of live demos. I honestly do not know why this is not working, because we did it last night, we activated it, and we tested it. And it was working, and I'm sure it's something silly, but supposedly once you get this notification, the connection is open. And since I have my, oh no, it's, upon requesting CryoCloud access, to which kind of access do you mean, Amy? Upon requesting being added to the team at the org, the only thing we control through the org is access to the team. So I'm not sure I'm understanding your question.
Yeah, just, I'm kind of walking through that step with install and request CryoCloud GitHub access. And I was just curious, if you kind of authenticate and say, yes, I want to install and request on your organization to whatever, whatever that org you want to select, and you click install and request, does that, do the admins of that repo that we're trying to connect to, or that org, do they know that we're doing, that I'm sort of accessing that, or is there anything they need to sort of be aware of when that connection is made?
That's a really good question. No, I don't think the other, if you have been given org permissions to add apps into the org, now you need to have the right permissions in the org you belong to be allowed to install apps into the org. But if you've been given that permission, I don't believe the addition of a new app notifies other org owners that an app was added. But maybe it does, actually. Now that I think of it, maybe it does, actually. I think it does generate an email. I think when you install an app in an org, it does produce one of these like notification emails that goes, an app was added to the org. I believe I think I have seen it happen, but I'm not 100% sure.
Okay. Yeah, thanks. I was just kind of curious what to kind of expect there. Yeah, thank you.
Yeah. And Luis, for your question, yes. And in fact, this tool was created to avoid having SSH keys on the hub. In fact, part of the reason so it was explicitly a goal of designing this, that I was storing SSH keys on my hubs so that I could use them without going crazy typing my HTTPS access token. And I was driving poor UV crazy because he's like, no, this is insanely dangerous. You're putting SSH keys to the Jupyter org on cloud hosted servers. That is nuts. I don't want you doing that. So UV Panda went out and created this little tool that has proven to be incredibly convenient. And now we install it on all the hubs and it gives us this. I'm sorry for the little snafu. I did this last night. I was super tired. I tested it. It worked. I'm doing something stupid right now, but I don't want to waste people's time because we only have a half hour and I want to make sure that Tasha and Jessica have time to talk. The other thing that I wanted to mention is we do have a global shared folder where we can put data. Some users who have admin rights have read-write privileges into that folder. It's called shared read-write. Others have read access to it, but that's a place where we can put like common things that are needed for the hub, common files, common directories, shared data can be put there. Otherwise, for sharing individual folders between people or between teams, for now, syncing we think is the optimal solution because it gives you individual control without having to deal with Unix permissions. And so Tasha and Jessica, I think I should probably stop here, and then we'll get if we have 5 or 10 minutes at the end in Q&A. We also mentioned where do you go to like request new things, add sort of what is the process for following up further with the team. But I want to make sure that the two of you have good time for the tutorial of the content-oriented tutorial. Let me stop sharing here. And again, sorry about the little GitHub snafu. It works. I use it all the time, but obviously the time that I'm doing a fancy live demo is the time that I did something silly and it broke. So that's just life with demos. Sorry about that.
Cool. Yeah. Thanks, Fernando. We are going to get into a little demo about that gives you all some code for accessing ICESat-2 data from the cloud from NSIDC, and also a few other data products, including Sentinel-2, which is in a cloud optimized format. And I'm going to walk you through the steps to do all of this. You can follow along and do exactly what I'm doing, or this will be recorded. You can do it later. If you fall behind, that's totally fine. This is all going to be there, so you can go through it later. And yeah, I'll get us started by Jessica, I'm gonna show them how to access and clone the repo.
That sounds great.
All right. So if you start out, you'll need to get the code for the repo to clone it. So I'm going to start by getting onto the CryoCloud. I have a few other server options. I'm going to go with medium here. And that's pretty fast opening, I hope. Yeah. So y'all start with basically just the shared folder here. Admins get shared read write, and that allows us to add data that everyone can see in the shared folder. For this tutorial, you can go to the terminal there, and just like you would with anything with GitHub, you can do git clone, and you can grab the HTTPS URL for the repo, which is the CryoCloud website. This has the tutorial in it. So just copy that, paste that in there, and that's going to clone the library. You see it popped up over here in our folder. And we have the entire Jupyter book and CryoCloud website now. So I'm going to navigate to the tutorial that's under book, tutorials, and then there's two in here. As Fernando mentioned, we had some AWS permissions errors. So one will give you Landsat and how to access Landsat once we get those AWS permissions straightened out. And the second one here is for Sentinel. So you get kind of 2 for 1 at right now. I've given you code to be able to do both. So while that loads, Jessica, do you want to start us out?
Yeah, thanks for getting us all set up, Tasha. And as she said, this was a fast change, heroic effort by Tasha this morning to get some Sentinel-2 data in here instead of Landsat. But I encourage you to check both of them out, especially once the permissions issues are figured out. And that actually kind of gives me a nice segue into starting to talk about some of this, which is if and when you encounter any sorts of permissions issues or cloud data access issues, please make sure that you let us know about them. There are a bunch of folks from NSIDC actually on the call with us right now, and they, as well as the rest of us, really need to know about these issues in order to solve them. This is a very new space for most of us. And so if we don't know what problems people are facing, it's really difficult for us to solve them. And so with that in mind, I'll just get us started. So here we have our ICESat-2 and Sentinel-2 cloud data access notebook that Tasha is showing. There's a lot of text in here that we won't necessarily be covering in detail, but this is to make it so that it's a great piece of reference tutorial for you as well, to go back to and really be able to modify this to use it as you'd like. So the goals of this tutorial are to help us identify and locate some data in the cloud. And then Tasha is going to demonstrate how to open that data into some common data processing libraries. And so the first thing that we're going to do is we're going to import a whole bunch of packages that are for the various ways that we're going to show you how to access data in the cloud. And so that's what these first boxes are. And I'll jump right into the ICESat-2 part, where we're going to use the library that Fernando mentioned earlier, IcePix. IcePix came about to make it easier to programmatically access data. It has been designed with to try and make it as easy as possible to switch your workflows between working in a local or some type of local environment, or with a more traditional download workflow to working in the cloud. And so as you'll see as we go through and we get to our authentication steps, it's pretty straightforward to switch an existing workflow. So to start with, we're going to focus for our tutorial today on a large glacier in West Greenland, Sermekhulalik, which is briefly known as Jakobshavn Isbrae. You'll see it referred to as both throughout this tutorial. And what we're doing here is we're just defining the data set that we want to look at. So ATL06, we're going to look at the land ice data set. We have a KML that describes the region that we are interested in, that Sermekhulalik area. We're looking at the month of April in 2019, but we can expand or limit those dates to the scale of our analysis. And then we're specifically looking at the regional ground track 338. And so Tasha has gone ahead and initialized all those parameters for us. If we would like to, we can, and then the next step for us is to set up what's called a query object in the IcePix library. This line of code that she's running here is just loading some of the information about that KML that she'll use later in the tutorial. But we can go ahead and look at, create that query object. Built-in functionality allows us to quickly visualize that spatial extent. During the preparation of this, we found a bug in the IcePix code. So the next thing that's here is a quick workaround while the bug fix makes its way through all of the proper channels to be native into the hub in the future. So that's the next step. What Tasha is demoing here is the really cool interactive widgets features that are available in JupyterHub to let you see both the area that you've requested as well as explore a little bit more the map on a Landsat background. And so then the next thing we're going to do is to just quickly look at and using the open altimetry interface with IcePix's access into the open altimetry interface, we're going to just quickly get some data to just see what it looks like in this region. And so once this loads, we'll be able to see that we have some really great data here. We've picked a cloud-free set of cloud-free paths. So we can check this data out quickly here. Here are the different, we're just looking at the different elevations of the ice surface. And now that we know that this is actually the data we would like to work with, we can go ahead and get those granules from, access those granules in the cloud. And so the nice, easy way to do that in IcePix is to simply set cloud equal to true when we're looking up our granule IDs. And then this will return for us a list of all of the granule IDs that correspond to the data that we're interested in. We're going to go ahead and we have to log into Earth data. And a huge shout out to Luis, who is on the call, and another team and a team of folks across multiple DACs who are all working really hard to make this authentication as simple as possible so that we can minimize some of those various permissions issues that we so often run into, particularly during live demos, as Fernando helpfully demonstrated for us earlier. So Tasha has logged in here for us, and now we can grab the credentials that we need. IcePix will, behind the scenes, create the extra credentials and tokens that you need for accessing data in the cloud. And then we can go ahead and set up our cloud file system and use that to access those granules by granule ID, the granules IDs that we got earlier. And so Tasha has gone and done this. We can see that we have been able to successfully open the file, no downloads required. Here's the information that's in the file. And then we're going to take our prior knowledge of the nested structure of ICESat-2 data to quickly load in some of this data with the HDF5 library for Python. to load in the data that we're interested in plotting later on in the tutorial. And we're going to load this specifically into a pandas data frame. And I believe now is when I'm passing things off to Tasha.
Yeah, so moving on from here, I wanted to point out that Pandas is this nice data frame, and we're going to continue to utilize that, and then we'll get into Xarray in just a moment. Can I get a show of hands maybe of how many people have used Xarray before? Yeah. Thumbs up or raise your hand. Decent number of people. But not everybody. Cool. So we're going to work a little bit more with pandas first and then get into Xarray. I'm going to load here. This is going to simulate you bringing data that you've downloaded and dropping it into our file folder. This data that we're going to be using is this ILATM over here. This is the airborne topographic mapper, ATM, and it's a LiDAR. And so we're going to co-register it with ICESat-2 data and show that in just a moment. Any information that you want for any of this is here within the text. So we're going to start by opening up the read CSV, which Pandas makes really easy. And it automatically takes the header from this file and makes that into the column names. And then each row is a measurement. And so you can see we have a ton of data here that includes surface height and a lot of different measurements. So we have a starboard port and nadir measurement, which is shown here in the tracks. And just to make things easy, we're going to only grab the track identifier 0, which is at nadir. And so that's what we're doing here, is we're only grabbing the data with that track identifier. And then to make it consistent with ICESat-2, we're changing the longitude, thereby getting about 2,000 measurements. And here we're going to visualize both the ICESat-2 data and the ATM data using our widgets. And we can see here we have that data plotted now. ATM is in orange and the ICESat-2 lines are in green. And if we zoom in, we can see that one of the ICESat-2 lines is kind of off on its own, but the other one is almost directly underneath ATM. So we can see that those are pretty close and hopefully will be pretty similar. Moving on, I'm going to show you an example of how to access and use cloud optimized data. So we're going to use Sentinel-2, but as I mentioned, there's Landsat example in the other tutorial. So the cloud optimized data is going to allow us to search and access and subset the data that we want without having to download or open all of the data. And there's a lot of different kinds of cloud optimized formats, but in general, they tend to read about 2 orders of magnitude faster. So we've seen people who have gone from working on their local computer, taking 5 hours to program to do some analysis on something in astrophysics, like looking at a planet. And then we put it in the cloud, do some work with non-optimized data formats. You can do that in like 5 minutes. So it makes a big difference if you're going to be using a lot of data to be using cloud optimized data. But those are not across the board available yet from NASA, but they're working on some of that. So Sentinel-2 and Landsat are in cloud optimized geotiffs. And so we're going to start by putting in some of our credentials for being a request or pays session. You have to do this to be able to access and open some data from S3 buckets. And then we're going to extract the geometry bounds that we already looked at before. And we're going to do a search of the Sentinel data, looking at the STAC API. So STAC stands for Spatial Temporal Asset Catalog, and it's basically a catalog that provides common metadata format for an entire data set to make it easier to index and query. So this is one of the things that speeds everything up here. We're going to do a similar search as we did before. We've got our bounding box, our time range. The URL is specific to whatever product you're using. So you do have to find these. And then for Sentinel, we want the specific collection. You'll put this specific collection here. You can do multiple, but this one's looking at Sentinel-2 level 2A data. And that goes into PyStack client, and we run that and we get 19 items. And we also produce that JSON file that we talked about earlier. Maybe it didn't run.
No, it is in /TMP.
Oh, it's temp. Yeah.
So you'll find it in the terminal because the file browser doesn't go above your home directory.
Yeah.
So if you go to
Okay.
/TMP at the terminal, it'll be there.
I'm gonna actually just run it in the main. German. There we are.
There you go.
So this is what came out of that. This is the search. And so there's 19 items. We're not really interested in that many. Each of the items, so this is an item collection. You can open this up and like visually look at each of the items that were collected, look at the metadata. So all that information is here and you can query it. We're going to open the JSON file into GeoPandas data frame so that we can visualize this here. So we're using GeoViews to do that, using some of the data from Sentinel, specific Sentinel columns. And I'm only visualizing 3 here, the ones that we're going to look at today. But yeah, this is a nice way to query this. You can look at the path row, or I guess it's the latitude band and grid square for Sentinel. So you can do that in widgets. And then we're going to use intake stack to access the data. So intake stack facilitates accessing by providing intake drivers for stack catalogs. And it's how we're going to get all of this into Xarray objects. So here's all of our items. And this is, using those scene IDs, being able to show like what the different data sets or bands are within a data set. And these are just different ways to query the data. So you can look at it and see what's available. I'm not going to go through each of these, but here it is again. And then you need to get the URL. And so for Sentinel-2, this is how you access the S3 bucket. In Landsat, it's slightly different. And now we're going to open that using the URL. So we're starting that session. So we're using those credentials we created earlier. And then we are putting that item URL in here and using Raster.io to open it. And Raster.io has an intuitive way of opening it. You can see we didn't say anything, but it's plotted the coordinates for us. And then we've also opened it into a NumPy array. You can do all of that with Raster.io. So that's pretty cool. Now I'll show you Xarray, which is really similar in nature to Pandas with slightly different commands and functions. So this Xarray uses Raster.io to open into Xarray. So Xarray, Pandas is 2D. It plots as a data frame. So you've got your columns and rows. And then Xarray is going to allow you be much better and faster for multidimensional data sets. So you can start to get into 3D, 4D, get your time, get your bands for all your different scenes and add all of these into one Xarray data set. And so that's what we've done here. This is just for one band. You can see the dimensions here. Now we have coordinates. So this is going to be each of our bands, our lat and our long, or X or Y. And then you've got different data variables in here that you can interrogate. We can also use RioXarray, which combines raster IO and Xarray, and does even more for us intuitively. So now we have all these attributes here. We've read in the scale factor, a lot of metadata gets added without you having to do anything if you use RioXarray. And there's some other functionality for that. Now to start reading in a lot more data, we're going to use Dask. And so Dask is our way of being able to chunk the data into small pieces so that we don't have to read all of it. It'll just read each chunk individually. And Dask allows us to also parallelize. So when we want to start doing bigger jobs, we're going to be using Dask. And Dask does all of this in all of its reads in a lazy way, so that when we start to open our data sets, it's not actually reading the data. We can do a bunch of computations, we can subset, we can do all of this, and it's only doing that like in the background on the metadata. And then as soon as you press values or print something out or plot something, that's when Dask grabs all of that data. So that's the part that ends up being slow, but you're only reading portions of the data that you actually need and not doing all the computations in between. So it ends up being a lot faster. So here we're going to build this Xarray with 3 bands here and with just one scene. And so we've decided to grab these 3 bands. We are using chunks. This is what Dask uses to only read portions of the data. So you want to do that with multiples. Choose a multiple of what is native for Sentinel or Landsat. I think Sentinel is 512. Landsat's definitely 512. So we've used 2048. And you can append, it's grabbing each band, it's appending all of those together, and then it's concatenating them over the new dimension band here. And so that's how you build an Xarray. And you can look at a lot of this data like pretty easily. It's very intuitive. And here's a few different things that you can access. Here's the lat, the X dimension. Here's the attributes that you can look at. The coordinate reference system. You can grab just one band using .cell, and you can say grab like the average for a band, which is now going to be calculated. So when you just took the mean and didn't want to actually see the number, it was very fast. Now you want to see it all calculated. Now you get your mean. So now we're going to do this for 3 scenes really quickly. And now that we're adding a time to this, we're going to create a time variable that we're going to add at the end of all of this when we're concatenating all the different scenes together. And we're grabbing that date time data from the GeoPandas data set. And then we're gonna look for what bands that we want from Sentinel-2. And we've decided that we want everything that has a resolution of 10. And here's the different ways that you can, this is the way that you can access that data and query it. And then it's going to print out all the different bands and their resolutions. And if we look at band names, it's only grab 4 of those because those are the only ones that are 10. So you can use that to only grab a few bands if you want that. Then we're going to grab those bands for the scene IDs that we've asked for from before. And so we're going to, again, grab each band, append all of them together, concatenate them along the band dimension, and then we're going to append all of the scenes together, and then we're going to concatenate them across the time variable. And that's going to give us a much larger Xarray data set that's 3 by 4 by a lot. And then we can also subset. There's a bit more functionality. You can subset by lat and long by deleting this here. but I'm not going to show that today because I haven't put in the new coordinates for the Sentinel coordinate system. But you can subset the data to whatever bands and scenes you want. This is the date times that you're choosing. This is the bands you're choosing, and this is how you add those. So yeah, so that's kind of in a nutshell how you can use some and access some of the data in the cloud, and also to add your own data as well. And a little bit of functionality from Pandas and Xarray at the top of this tutorial. The notebooks that were kind of combined to create this are there, and they have a lot more on Pandas and Xarray functionality if you want it. I do want to give credit. So Jessica and I also made this. Zach Fair and Ian Joggin of the ICESat-2 Hack Week contributed a lot to this. So, and Brad Lipovsky. So there's a lot of people who've put work into that. So do I have any questions?
So Tasha, I guess we have 5 minutes. I think the only thing, and you closed your screen share. So I think the only thing that I wanted to show, either or you can show it if you have it there, is kind of the issues tab on the Hub image repo, and as the place where I mean, there's been already questions of how do I add a package, how do I configure if I need something. So just to let them know that this repo on the Hub image one
Yeah, let's go to the Hub image.
So that's the repo that basically defines the environment we're using. Packages, so app.txt has the packages. Here are the issues. If you kind of the three key files are those. Environment YAML has all the conda packages. App.txt has the Linux packages in the image, and start is the little script that runs at the beginning that does things like, oh, maybe you need to configure some environment variable or something. So if you see anything missing and like, oh, I would like tool X to be there, if you know what it is, feel free to submit a pull request. Weiji has done a terrific job. And by the way, huge thanks, Weiji, for all the work you've done on that repo already. And so if you know how to do it, feel free to submit a PR. If you don't, feel free to open an issue. And then we can work with the I2C team on filtering whatever's needed on that. And that's kind of how basically whatever happens in that repo is the system you're using. That's all I wanted to mention. But Tasha, otherwise, I'll leave it to you to kind of close with Q&A or whatever other topics of discussion you think are relevant.
Yeah, Dennis, you had a question?
Yeah. So first of all, thanks so much, everybody, for this awesome tutorial and getting us started. I'm really excited to see where this goes for our whole community. Tasha, up top, a couple of hours ago, you mentioned shared S3 cloud storage. So I know that that's not currently available, but I wonder if you could speak a little bit to where that's headed, when it might be available, and yeah, what the vision is, I guess, for the JupyterHub in terms of being a place where the science team can collaborate and share data, in shared S3 storage and things like that.
Yeah, so I think one of the main things that will happen or can happen, needs to happen, is that there's a shared GitHub repository for the ICESat-2 Science Team. That's going to be a good place for people to work from. And then in terms of storage, we've been talking with NSIDC and some other people. We're working on getting cloud optimized formats for ICESat-2 data. We're going to be one of the first platform that has that data, and we're going to need a place to store it that's potentially with NSIDC, but it costs money, so it has to be a discussion made by the ICESat-2 Science Team if it starts to get to be large S3 bucket storage. Yeah, so I think it's just a discussion going forward. When people have ideas of what they want to put in here or things that all of us are sharing, and it doesn't make sense to, be downloading that, we definitely want to hear about that, and we'll have discussions about getting that onto the cloud for you.
But so ultimately, there will be some kind of shared S3 storage that the whole CryoCloud hub can access. I'm thinking about things like intermediate data that our project is producing, for example, that we want to share within the project team. Is that what the NSIDC S3 storage will possibly be for, or no?
I think it just depends on what it is. Some intermediate stuff is going to be small enough you can just share it over sync thing. Some of it, when it needs to be in a large, when it's much bigger, then we might have to do that. We just don't have anything like specifically planned for sure. Yeah, so that's a potential for the future. Any other questions?
So I dropped the link on the chat, Tasha, to the discourse ICESat-2 Pangeo category. The Pangeo discourse forum is already set up. There's already in that forum also a lot of expertise about kind of doing geoscience in the cloud. So we figured that could be a good place to continue kind of more general discussion. So opening specific issues, like there's an issue with the hub package, we can do that in on the GitHub repo. But and obviously Jessica leads the ICEPIX team, and ICEPIX specific discussions and issues can be open on those repos. But we discussed a little bit, and this seemed to be, for at least for now, probably the best starting place for kind of a community forum for people to bring up sort of any general questions and kind of at least discussions that you're willing to have in the open. Pangeo the Pangeo forum is a good place to talk.
Yeah, lots of opportunities for open science, and it gets to be really cool when you're working, like late at night, collaborating on things, or like, I mean, when other people are on and doing a bunch of coding with you, it gets to be really fast paced and really productive. It's been really fun working with the open science community. We're right at noon, or noon here at the hour, wherever you are. So I want to let you guys all go. I will mention the slides that we had today, we're going to publish on Zenodo, and we're going to send out links to. They'll be available on the Jupyter book, and the tutorials are there as well. And we will continue to upgrade and add more things to that. There will be instructions for how to contribute to the Jupyter book, how to do all of these updates to the Docker image that we talked about. All of that will be on the Jupyter book, so you can access it there. And then please, please, please finish your surveys and cite us if you are using CryoCloud, and publish. I think that's it.
Thanks, everyone. And yes, please open issues as you see them on the repo, ask questions on Discourse. We will be watching both of those repos, the hub image one more for like system stuff, and the Cryo and the Cloud website for like content on the book. But you're also welcome to contribute to both of them, right? This is a community effort, and we build these things together. So thanks everyone, and again to those who did all the work in the back to make this possible. Thank you, and James, please pass on to the 2I2C team our thanks. They worked really hard to make it possible, and for all your attention. I hope to meet some of you in person at some point.
And thank you very much, Fernando.
No, this is wonderful, and I couldn't be happier. All right, I'm going to switch to my next meeting, and I'll upload the recording later. I'll upload it. Oh, we'll have to decide what. I have the recording. I'll share it later, and then we can see where we put it permanently.
Cool.